afternoon, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, we are going to continue our previous lecture, that is interval estimation. So, let us move into the details. So, let us recap what is an interval estimator. There are two different kinds of estimators in statistical estimation, namely the point estimation and the interval estimation. That means in order to estimate the descriptor of population, suppose this rectangle represents a statistical population and we are interested to estimate the value of mu. For that, we'll take the help of a sample which is subpart of the population and we'll try to take the help of a sample statistical formula, and with the help of x bar we'll try to estimate the value of mu. So this will be done in two ways, namely the point estimation and the interval estimation. Under point estimation, we'll state the value as a single number, that is the average height of the students of a college is 65 inches or 5 feet 6 inches, like that. So that is called point estimation. Under interval estimation, we'll try to express the value of mu as an interval. That means we'll state as the mu will range between 60 inches to 70 inches. That means we'll represent mu as an interval 60 to 70 inches. This is called interval estimation. So interval estimation will gives us an advantage that will have a flexibility of having a margin, of course it is not as precise as the point estimation, but we'll have a flexibility of giving a margin towards the right and the left. That is called interval estimation. So interval estimation is an important aspect of inferential statistics, and we are going to see some applications of interval estimation. Before that, I'd like to recap these things. Interval estimates are all the ranges an interval estimator can assume. That means in the interval estimation, you'll express the value of the population parameter theta as an interval. It can be any range. The range can be a rational or irrational limits, or natural numbers, or integers, with whatever you can assume any kind of real numbers as the limits of the interval. And each interval estimates states and range within which a population parameter probably lies. That means if you say that the interval estimation of theta is some a and b, that means you are saying that theta has a very high probability, say 95% or 99% of probability, that theta is going to fall in the interval closed interval a. So in the interval estimation, we express the value of the population parameter theta as an interval, but to some possible extent, which is called the probability of confidence, like 95% of confidence or 99% of confidence. And an interval estimator can be assessed through two dimensions, that is accuracy and precision. That means first we'll try to find uh, how distant the mu will fall from x bar. That means what is the range towards left and right, x bar minus c or x bar plus c. Okay, that means when we try to estimate the population value mu with x bar, okay, there will be some difference between x bar and mu, right? X bar need not be equal to mu. So we'll try to estimate the range within which mu will fall from x bar, that is towards the left and towards the right, and that is called the confidence level or confidence. And precision means if we are able to reduce this e, that is the error between x bar and mu, the possible error at 1 minus alpha probability, okay, that is called the maximum error. Okay, If we are able to restrict this E as least as possible, then we can say that we are more precise. That means E should be very, very meager or mere or like 2% or 1% or even half percent. Then we say that we are more uh, nearest to the original value of the parameter. So these two plays an important role in deciding the estimation, the level of estimation we have done using the sample in order to estimate the population parameters. Now, as in the last class, we have seen that to estimate the population mean, that means the average height of the college or the average weight of the students of a college or average IQ level of students of the college. Okay, and we depend on the sample average, that is x bar. Say in a college there are 5,000 of students, so we'll take a sample of 500 students. So the average height of 500 students is represented by x bar, and the average height of 5,000 students is represented by mu. Okay, now as I said in the last class, there are two important qualities that an estimator should possess in order to be called as best estimator. That is unbiasedness, unbiasedness, and and efficiency. Efficiency. Okay, unbiasedness means x bar will be said as an unbiased estimator of mu if expectation of x bar is equals to mu, which is verified here. Here, x bar is calculated from the sample with the elements x1, x2, so on, xn. Then E of x bar will be E of x1 plus E of x2, so on, E of xn by n. So, you know that expectation of each element of the population is always equals to mu. So, this becomes mu, so on. The last value also becomes mu, and hence we got n times mu by mu, and hence we got. So, what we have proven? We have proven that E of x bar is always equals to mu, and hence we found that the sample mean is always an unbiased estimator of an unbiased estimator of the population. Okay, okay. So this is what we have arrived at. That means whenever you try to estimate the value of mu, okay, with the help of x bar, the data will be spread equally on either side of the x bar. That is what you are saying. Unbiased means the data will be spread equally on either side of x bar. That is what you understood. If it is biased, the graph will be like this. See here, uh, this is mu, and this is x bar. Let us suppose that x bar. Here you are seeing that only 20% of the data is on left side and 80% is on the right side. So here this parameter, say this is theta 1, this is theta 1 is said to be not unbiased estimator of theta, but whereas x bar is always an unbiased estimator. So in this way we can distinguish between the unbiasedness and biasedness of estimators. Now coming to the efficiency. Suppose there exist more than 3 unbiased estimators of the population parameter theta. Suppose we are trying to estimate the population parameter theta with the help of 3 sample statistic formulae called theta 1, theta 2, theta 3. That means 3 are unbiased means we have expectation of theta 1 is equal to theta, expectation of theta 2 is equal to theta, and expectation of theta 3 is equal to theta. All these are unbiased. Now, how to find the best one among these 3? For that, we need one more criteria called efficiency. Let us look into that details. Efficiency can be understood diagrammatically with the help of following graphs. See here, we are trying to find the value of mu with the help of x bar. Okay, here also we are trying to find the value of mu with the help of, say, same theta. This is theta 2, this is theta 1. Okay, now here either side of theta 1 the data has been spread equal, right? Here also either side of the theta 2 the data has been spread equally. But if you carefully observe, here the it is little high peaked and less, it is occupying less space and containing whole the data when compared to this graph. That means here the tails are spreading too wider. The tails are too wider. Here the tails are too little narrow. That means here you can store the whole data within less space. But here you need more space to store the data. This is due to the standard deviation. Here the standard deviation is high, sigma 2, here sigma 1. The spread or the range or the spread of the data theta 2 is greater than theta 1. That is why theta 1 is called as more efficient estimator than theta 2. So in this way we could distinguish among the different kinds of estimators with the help of two criteria called unbiasedness and efficiency. Now here we are seeing some examples that the modified sample variance cap s square, which is given by xi minus mu whole square or x bar whole square with divide by n minus. Instead of n we use n minus. This here you find that E of s square is always equal to population variance, and hence this modified sample variance is called the unbiased estimator of population variance. Say this is S bar. But if you replace this with regular sample variance, that is xi minus x bar whole square by n, it E of s square is not equal to sigma square. That means the regular sample variance is not at all an unbiased estimator of population variance, but the modified sample variance will be an unbiased estimator of the population variance. Okay, and similarly, you can observe that the SXY will be an unbiased estimate of sigma xy or covariance of xy. You know, covariance you have come across in your correlation regression. Similarly, some examples of unbiased estimates are the sample covariance with modified n with n minus 1 will be an unbiased estimate of the population covariance. Okay, and here you are just in the last class as we have discussed here, the modified variance s square summation xi minus x bar whole square divided by n minus 1, and we have calculated E of s square and we have arrived at that the value is sigma square, and hence we declare that s bar square is an unbiased estimator of the population. Now we are coming to the interval estimation. Okay, after this discussing the types of estimators, now we are entering the interval estimation and the confidence interval, these kinds of work. Before that, I'd like to discuss one important concept called 1 minus alpha or the confidence level. What do you mean by the level of confidence? What do you mean by the level of confidence? See, when we are trying to estimate the population parameter mu with the help of the sample statistic x bar, with the help of sample statistic x bar, okay, generally there will be some error. Okay, there will be some error. X bar need not be equal to exactly equal to the mu. So, but if we are confident that the difference between x bar and mu, that is the difference between x bar and mu will be less than very little epsilon, specified epsilon. Okay, the probability that the difference between x bar and mu will be less than or the very little epsilon is called the level of confidence. Is called the level of confidence. That means, suppose if we say that the level of confidence is 95%, in estimating the population parameter with the help of given sample. That means we are confident that our sample calculation resulted value is going to equal with the original mu, population value mu, and we are confident that 95%. We are 95% confidence. We are saying that x bar will be equal to mu. Okay, there will be very minute error epsilon. That is what do you mean by confidence error. If we say that the confidence level is 90%, that means we are confident that 90% confidence that our x bar is going to be differ with mu with a very minute difference epsilon. Okay, so on the other side, you are confident 95%. You are confident about your calculation that x bar is going to equal with mu with a less difference, with a minute difference epsilon. That means you have a doubt of 5%. That is called level of significance. That is called level of significance. So there are two probabilities, namely level of confidence and level of significance. Level of confidence is the probability with which we are ascertaining that our estimated value is going to be almost equal to the required population parameter. And level of significance is that the probability with which we are doubting that our estimated value will differ from the original population value more than epsilon value. Okay, that is what. Now, with the help of this level of confidence, we can construct a precise interval around x bar for the value mu. Okay, let us see how. So we are going to construct a formula called the confidence interval or confidence interval of mu around x bar, around the sample mean x bar, uh, at 1 minus alpha level of confidence. Okay, LOC means level of confidence. That means at 95% confidence, what will be the difference between x bar and mu? Okay, that is what the formula says. Okay, for this, we'll take the help of the central limit theorem, which you have come across in your probability and statistics. Let us recap that. So 1 minus alpha. So probability of our x bar will differ from the mu. Okay, um, less than a precise value e is 1 minus alpha. Okay, that is what we are writing, 1 minus alpha. Now, when we understand the meaning of mod x less than, mod x less than a, what do you write? Minus a less than x less than. So with this, we arrive at that. We can write it as x bar minus mu by sigma, okay, by root n is less than epsilon by sigma by root n is equal to 1. It means we are scaling on either side, we are dividing the sigma by root n, then we get that mod x bar minus mu by sigma by root n is less than e by sigma by root n. What is sigma here? Sigma is the standard deviation of the population. Sigma is the SD of population and n is the sample. We are trying to estimate the population with the help of a sample of size small n. Okay, this is x bar, this is mu, and the size of the sample is n. Okay, so we are dividing the standard deviation under the ratio of root of positive square root of the sample size. So x bar minus mu by sigma by root n is less than e by sigma by root n. Now, from central limit theorem, we call it as z bar. So p of z bar is less than epsilon by sigma by root n is 1 minus alpha. Okay, now we got z bar is less than, or z bar is less than epsilon by e by sigma by root n, and the probability is 1 minus alpha. Now, if we take this to the if we multiply on either side with sigma by root n, we get z bar into sigma by root n, okay, is less than e is 1 minus alpha. Okay, so this particular value is is represented with E, which is called the maximum possible error. That is called Z alpha by 2 sigma by 2. So this motivates us to define the maximum possible error between x bar and mu, okay, which is called the maximum possible error or marginal error E, which is represented by Z alpha by 2 sigma by root n at 1 minus alpha level of confidence. And with this, we define the interval of mu falling around x bar is x bar minus E, comma x bar plus E. That means we are saying that with 1 minus alpha percentage of confidence, mu will fall between, will lies between x bar minus E and x bar plus E. X bar plus E. That is what we are saying. Mu will fall between x bar minus E, x bar plus E, and our confidence is 1 minus alpha, and E is the error between x bar and mu, which is estimated with the help of formula E is equal to Z alpha by 2 by sigma by 2. And this interval is called the confidence interval of mu around x bar at 1 minus alpha level of confidence. Okay, now let us look into some applications of the confidence interval. So here we had a problem. To estimate the average time it takes to assemble a computer component, an engineer timed 49 technicians in the performance of this task, getting a mean of 12 minutes and standard deviation of 1.90 minutes. According to the data, there are several engineers working in a hardware networking company. So suppose TCS has several number of thousands of software hardware networking engineers. Okay, so in order to estimate their efficiency, they are conducting a test. They have randomly picked 49 hardware experts, and they have given a task to all the 49 experts that they have to assemble a particular computer components. Okay, and they will calculate the time they are taking to assemble the computer components. That means each person out of 49, every person will be given a set of computer components, and they have to assemble and they have to form a computer. Okay, so they will calculate the time within which they are able to perform the task. So in their survey, the 49 technicians have taken on average 12 minutes of time to assemble the computer. So they are able to assemble the computer, okay, in a complete way, and the time taken by them is 12 minutes on an average with a margin of 2 minutes. That means plus or minus 2 minutes. Some people may have taken 2 more minutes, and some people may have taken 2 less minutes. That means they have finished early. Okay, so like that we are estimating that 10 to 14 minutes. Okay, that is what about the sample survey. Now, by using this data, we have to construct 99% confidence interval for the average time taken by the whole TCS employed network engineers to assemble the computer components. There are several thousands of hardware experts working. So, we want to estimate the mu, that is the average time taken by the whole network engineers working under TCS. Okay, at 99% of confidence, what will be the time range they will take to assemble the computer? Okay, and second, with what confidence we can assert that the sample mean does not differ from the true mean by more than 15 seconds. That means we have a sample of 12 minutes, right? And generally it differs from mu, the original population average. Okay, what is the confidence that the difference will be less than 15 seconds? Okay, we have to find the corresponding the level of confidence, that is the probability 1 minus. Okay, this is the question. Now let us try to solve this. Okay, so here first let us list out all the given data in terms of mathematical terminology. Here the sample mean time to assemble the computer taken by 49 workers is 12 minutes, and the number of workers we have tested is 49, that is the sample size is 49, and the standard deviation is 2 minutes or 1.9, approximately 2 minutes. Okay, now we have to find the first bit. We have to find at 1 minus alpha 99% confidence. We have to find E, and then we have to find the interval x bar minus E comma x bar plus E. That is the first bit. Okay, we have to find the precise confidence interval. Right. For that, first we'll start with how to find E. For that, we need Z alpha by 2. Z alpha by 2 at 99% confidence. In the last class, I have given you the values which we have to note it, which we have registered. Z alpha by 2 at 99% confidence is 2.58. Okay, of course, we had a formula. Z alpha by 2 can be calculated with the help of the formula A inverse of 1 minus alpha by 2. Okay, that is Z alpha by 2 can be calculated A inverse of 1 minus, that is 0.99 by 2. That means A inverse of 0.495. This is equal to 2.58 according to the normal tables. So what do we confer? We have, so as 49 workers are tested and the average time taken by them is 12 minutes to assemble the computer with a standard deviation of 2 minutes. We found that Z alpha by 2 is 2.58. Okay, now we are ready to find the maximum possible error between x bar and mu, that is E Z alpha by 2 sigma by root n. That is 2.58 times sigma. Sigma is 2 minutes by root n, n is 49. So it will be 2.58 means 5.16 by 7. 5.16 by 7. Okay, and approximately it results into 0.7 something. So maximum possible error is 0.7. Now with this, we'll find the confidence interval x bar minus E comma x bar plus E. That is 12 minus 0.7 comma 12 plus 0.7. That is 11.03 comma 12.07. That means we are saying that the average time taken by the whole workers and working in TCS to assemble the computer components will range from 11 minutes to 12.07 minutes. That is what we are estimating under 99% of level of confidence. Now, let us look into the second part of the problem. See, in the second part, as per the data, we have 49 workers and x bar is 12 minutes and standard deviation is 2 minutes. That is given in the data. But in the second bit, we are given that the sample mean x bar means difference from the true mean, that is mu, will not be more than 15 seconds. That is equal to 15 seconds. The difference between these two will be 15 seconds. Okay, and what is the probability of having the difference between x bar and mu will be less than 15 seconds? That is what we are asking to find. So we take this as maximum possible error is 15 seconds. Let us convert 12 minutes into seconds. 12 minutes means 12 into 60. Okay, that means 720 seconds. And standard deviation is 2 minutes, that is 120 seconds. Now we have maximum possible error 15. Let us write the formula Z alpha by 2 sigma by root n. So here E is equal to Z alpha by 2 sigma by root n. E is 15 seconds. Z alpha by 2 we have to find, and sigma is 120 seconds. Okay, and n is root 49. Okay, so Z alpha by 2 is equal to 15 into 7 by 1. Okay, so we'll get 105 by 120, right? That means 7 by 8. And we know that Z alpha by 2 is nothing but A inverse of 1 minus alpha by 2. That is equal to 7 by 8. Implies 1 minus alpha by 2 is equal to A of 7 by 8. What is the value of 7 by 8? If we divide 7 with 8, we will get this value as 0.8 and 7, 0.87. So by using the normal tables, we get this value as around 1 minus, that means 1 minus alpha by 2, around 45%. And hence we get 1 minus alpha as around 90% or 88%. That means we are saying that with 88% confidence, we are saying that the difference between our estimated 12 minutes and the original population mean mu will be less than 15 seconds, and we are confident that 88 to 90%. That is what we ascertain from this problem. Now we'll see one more application to understand the interval estimation and the confidence interval more impactful. Next, here we are asked to construct 95% LOS and 99% LOS for the problem where a random sample of 100 students gave a mean weight of 58 kg. Suppose in our IARE there are 4,000 students. Now we have taken 100 students sample. The average weight of these students is 58 kgs with a standard deviation 4 kgs. Okay, that means most of the students in this sample are having the body weight of 58 kgs with a margin of 4 kgs. Okay, now we want to find the interval of mu around this x bar, okay, at 95% and 99% confidence. So I'll explain the 95%. So we have 1 minus alpha is equal to 95%, that is 0.95. So 1 minus alpha by 2 is equal to 0.475. Okay, 0.475. So A inverse of 1 minus alpha by 2 is equal to A inverse of 0.475, that is equal to 1.96. Okay, so we got A inverse of 1 minus alpha by 2, that means Z alpha by 2, we got 1.96. So what did we obtain? From the given data, 95% level of confidence, we obtained that Z alpha by 2 is 1.96. Now, let us try to calculate E, Z alpha by 2 sigma by root 10. That is 1.96 into, what is sigma? 4 kgs by what is the sample size? 100 students, root 10. Okay, or root 100, sorry, root 100. That means we have 1.96 into 2 by 5. Okay, and hence we have 0.37, that means 0.75 approximately. So what is the maximum possible error between x bar and mu is 0.75. Okay, now the confidence interval is x bar minus e comma x bar plus e. That is 58 minus 0.75 kgs to 58 plus 0.75 kgs. That is approximately 57 kgs to 59 kgs. That means we are telling that the whole IARE students, the average weight of all the students in IARE will range from 57 to 59 kgs at 95% of confidence. In the similar way, you can find the confidence level of the same problem at 99% also by proceeding in the same ways. Now, at the last, we'll see one more application with which we are going to conclude the lecture. So first, let us recap and remember these things. The table value or Z alpha by 2 value at 1% level of confidence, or alpha 1%, alpha 2%, alpha 5%, alpha 2%. Or you can also understand it as 1 minus alpha 99%, 1 minus alpha 98%. 1 minus alpha, 95%. 1 minus alpha, 90%. We have table values correspondingly 2.58, 2.33, 1.96, 1.6. Okay, we have to remember them as formula. Now, here we are going to see one more interesting application of confidence intervals to find out to fix the sample of size to be collected in order to restrict the error to the prescribed level. See here, if the maximum error about means the probability 0.95 is 1.2. That means you are expecting that the error between x bar and mu will be 1.2. You should not be exceeding 1.2. And you are precising with the level of confidence with 195%. That is 0.9. Okay, and standard deviation is given as 10. Standard deviation is given as 10 marks. We have to find sample size n. What is the size of the sample? That means we have to find the sample size. Okay, so let us see how we will handle this problem. First, we have 1 minus alpha as 0.95. That means 1 minus alpha by 2 will be 0.475. A inverse of 1 minus alpha by 2 will be A inverse of 0.475, that is equal to 1.96. Okay, so what do we get? We get Z alpha by 2 is equal to 1.96. Okay, now when we have Z alpha by 2 is equal to 1.96 and we have sigma, we let us consider the E formula, that is maximum error Z alpha by 2 sigma by root n, that is equal to 1.96 into what is sigma 10. Okay, and we don't know the n, but we know the E. What is E? We are expecting that E will be less than 1.2, so we take E as 1.2. So root n is equal to 1.96 into 10 by 1.9. That is root n is equal to 19.6 by 1.2. That means root n is equal to 196 by 12. That means root n is equal to what do you say? 5 12s are 60, 10 12s are 120. So 16 around. So n is equal to 4 or 16 square, that is 256. So what do you say? Have to collect a sample of size 256 in order to restrict your error between x bar and mu to a maximum of 1 point. Okay, so from this problem what do you conclude? In order to restrict the difference between x bar and mu less than 1.2 at a confidence of 0.95, okay, where sigma is 10, you have to collect a sample of size 256. That is what we are obtaining. So here it's like a two-sided weapon, two-edged knife. With the help of confidence interval, we can assess the confidence interval 1 minus alpha. As well, the same formula can be used to find out the sample size n. Okay, when 1 minus alpha given. So when 1 minus alpha is given, we'll find the sample size n. When n is given, we'll try to find the 1 minus alpha and we'll try to estimate the interval capital E. Okay, and the same way you can understand this problem where 100 measurements of breaking strength of cotton thread give a mean of 7.4 and 1 point standard deviation of 1.2 grams. That means you have taken 100 measurements of breaking strength of a cotton thread. Okay, and the average breaking strength is 7.4 grams and the standard deviation is 1.2 grams. So this is x bar, this is sigma. Okay, and 1 minus alpha is 95% and n is equal to 100. With the help, you can find first you will find z alpha by 2, a inverse of 1 minus alpha by 2. That will be 1.96. And then you will calculate E is equal to z alpha by 2 sigma by root n, that is 1.96 into sigma, that is 1.2 by n, that is root 100. And this gives maximum error. And with the help of maximum error, you will calculate x bar minus e and x bar plus e, which is called confidence. Suppose if you try to calculate this, this will be 10. So uh, the value becomes 0.196 into 1.2. Okay, that means you will get approximately maximum error will be 2, and hence x bar minus e means 7.4 minus 2 comma 7.4 plus 2, and hence it will be 5.4 to 9.4. That is, you are expecting that the average mean of the whole population will fall between 54 to 94 with 95% of marks. In this way, we can calculate the confidence interval of mu around x bar with the help of formula x bar minus e, x bar plus e. Okay, where e is given by the formula z alpha by 2 sigma by root n. Here e is called maximum possible error between x bar and mu, and z alpha by 2 is called a inverse of 1 minus alpha by 2, where 1 minus alpha is called the level of confidence. Okay, in this way we can assess the confidence interval within which mu is going to fall when a 1 minus alpha given. So let us summarize the things. There will be three important things: n, 1 minus alpha, and maximum error. If n and 1 minus alpha is given, we have to find maximum error. If n and e are given, we have to find 1 minus alpha. If 1 minus alpha and e are given, we have to find the sample size. So there are three different kinds of variations. So by using any two of this triad, that is n, 1 minus alpha, e, when two things are given, we can go for the third thing. That is the advantage of confidence intervals. Okay, with the help of this, I'd like to conclude the lecture for today. And in the next class, we'll read with the next concept. And thanks for your patience listening. I'm signing off. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.